Great. Thank you, Antonella. Can you hear me?
Yes.
Perfect. So thank you. Thank you so much. I'm very excited to join you all and talk about finding rare gems. This is such a timely topic, and just kudos again to all the organizers for putting together this fantastic program. So for the first part of my talk, I'll be focusing on dual and binary supermassive black holes. Traditionally, this field has been driven by theory, but recent years have seen growing excitement in the observational community as well. So this is a category of known rare gems, so we know they're there, especially I think in light of the recent PTA results on the first direct detection of the stochastic low-frequency gravitational wave background. Just to clarify some terminology for dual systems, I mean black holes that are sitting in the potential wells of their host galaxy stars with kiloparsec or sub-kiloparsec separations. For binaries, I mean they are gravitationally bound directly to each other, typically with sub-parsec separations or smaller. So these systems typically thought to form through galaxy mergers and often involve one or two active galactic nuclei. So I'll be focusing on unobscured or type 1 sources just because they're easier to observe. However, we all know that the obscured population may be even more common, as I believe Stephanie mentioned in her talk on Tuesday. Now, so I'll highlight some recent work done with current facilities and then end the first part with a brief outlook on the prospect with upcoming surveys. For the second part of my talk, I'll introduce a data-driven tool we've been developing called DeepDisc. So DeepDisc is led by grad student Grant Merce at Illinois, aiming to be a general purpose tool for discovery, instance segmentation, classification, and other physical inferences with the ultimate goal to explore the uncharted. Okay, so I know we have a sophisticated audience here, but I want to start with a few words to provide the big picture and motivate my talk. So the multi-messenger and time domain is a key priority for the coming decade, as we all know, with LIGO fulfilling the promise of gravitational wave astronomy, and most recently pulsar timing arrays, and a little bit further down the road with LISA will open up new windows, reveal unknown rare gems eventually, hopefully, much like the first X-ray and radio telescope did. And with this big backdrop, dual and binary massive black holes are among the most important sources for both PTA and LISA. Now, you may wonder why we need LISA when we already have LIGO. So the answer lies in the unique nature of gravitational waves from these supermassive mergers. So detecting these will be unlike any other black hole mergers we've heard before with LIGO. So most, if not all, stellar mass black hole mergers from LIGO seem to have no accompanying EM counterparts. However, unlike their smaller counterparts, these massive mergers expected to occur usually in gas-rich environments, which potentially means that they will produce bright EM counterparts, providing a wealth of additional information. So another major difference between LISA and LIGO binaries is that LISA is designed to detect mergers in slow motion, so meaning starting from the inspiraling phase. And this allows LISA to provide forewarning to EM and particle detectors for a more comprehensive MMA observation. And additionally, EM observations will help LISA localize sources and measure their redshift and forecast and interpret the signals more accurately. So complementary EM observations are really crucial. Now, just to, I think, give a broad brush picture. So complementary probes at various scales are essential for our understanding of the full picture of the evolution of these massive binaries as they progress from galactic to subgalactic, all the way to subparsec and milliparsec scales. So before diving into the details, I'd like to draw an analogy with detecting stellar binary stars and exoplanets. So basically, we can borrow inspiration from every technique used in these fields. So thank you to the the pioneers in these other fields. So I will highlight three main regimes roughly in the reverse order along the merger sequence. So we'll start with the really small scale milliparsec scale binaries. So these will potentially be detected with T-like curves in future, which is the most closely related to emitting gravitational waves. And I'll talk about subparsec scales. And this is using radio velocities measured from these time domain spectroscopic surveys. And finally, I'll zoom out to the subgalactic and galactic scales where we have the most robust evidence. Okay, so this example here is from a numerical simulation, which are there are a bunch of them, but a common signature is these quasi-periodic light curves due to modulation of the accretion rate from the binary torque. Alternatively, these quasi-periodic light curves could also be due to either Doppler beaming or self-lensing when the accretion rate stays constant. So this gives us a way to potentially find these systems through light curves. A major challenge, I think, has been discussed in this meeting is, however, we know that AGNs vary stochastically. So it's very difficult to distinguish quasi-periodicity from red noise stochastic variability, and especially with very noisy light curves that have uneven sampling and limited time baseline. So to address this problem, we combine data from the SDSS STRAP 82 survey with the dark energy survey, and then now with our dedicated long-term DECAM programs. And this is led by a former grad student, Tony Chen. So compared to previous studies, our results are likely to be more robust because our combined time baseline is 2 to 5 times longer than previous shallower surveys over larger areas. So from PTF, ZPF, CRTS, for example, and at much higher sensitivity. What I'm showing you here is an example candidate displaying potential quasi-periodicity. So the total time baseline here spans about 5 cycles, which is the bare minimum, which I emphasize for rejecting false positives due to red noise. So we're still further extending the time baseline and increasing, the statistical significance with dedicated long-term monitoring with DECAM before LSST take over. So I think it really highlights the importance of combining multiple surveys and data sets to really maximize the robustness and the potential of real discovery. Now, switching gears to subparsec scales, where we monitor the velocity offsets between narrow and broad emission lines, which trace the host galaxy and the active black hole in a binary. So as shown by this cartoon here, this is analogous to the radio velocity technique used in exoplanet detection. And using repeat spectroscopy from the legacy SDSS, we've discovered some of the most promising candidates for subparsec binaries. So I'm only highlighting our current work with Sloan Phi, which we use to further monitor the radio velocities of candidates, but also rule out alternative explanations such as due to broad emission line kinematics. And I know, so there are also others. So for example, Antonella and her group, I know they're also finding these systems using DESI, for example. The difficulty, however, is that the typical orbital period of these binaries are expected to be, at least centuries, which are too long to cover fully. So we only have candidates and some, statistical constraints for the population. And I want to highlight a work being led by another grad student, Liam Nolan. So Liam is conducting a comparison study with a carefully matched control sample of ordinary AGNs and quasars and leveraging the HST archive. Again, emphasizing, I think, the importance of combining existing data sets with, the candidates of these rare gems we find. And so the eventual goal is to find complementary evidence either for or against these candidates to be able to, I think, thoroughly test this hypothesis, right? So I think finding rare gems or, in searching for them is only the first step. I think a common theme has been already discussed in this meeting. And so what Liam found was a, tentatively higher fraction of galaxies with more disturbed morphology and structural properties, potentially could due to post-mergers in these radial velocity selected candidates. So I think the result is very encouraging, but again, so it will need much better statistics to be offered by these upcoming surveys. Now, zooming further out, we have dual agents on galactic and subgalactic scales. So at this phase, we can directly resolve the two black holes, and then there's already significant, direct observational evidence in the low redshift universe. However, most previous works were relatively limited to the low redshift and low luminosity systems, and we want to study the high redshift and the high luminosity regime where mergers may have a bigger impact. For this, we have developed a new technique called astrometry or variability-induced astrometry, leveraging Gaia's precision astrometry. So it's very similar to looking at a railway crossing sign from a distance, so as being illustrated here. So there is an apparent jiggling effect due to the asynchronous variability of two unresolved point sources. So using this technique, we've followed up with Hubble high-resolution dual-band optical imaging, a large sample of these rare gem candidates that have high astrometric excess noise from Gaia. And this is the Hubble program led by Xiangqi Huang, now a postdoc fellow at IAS. So here are some examples. So the left show the low resolution ground-based images, while the right shows the follow-up Hubble images. And it really, I think, demonstrates the feasibility of this technique in finding doubles or even multiples that appear as unresolved in lower resolution images. And I'm showing you a particular example here in which we have done extensive follow-ups, including very deep near-infrared imaging with Hubble, as well as IFU spectroscopy with JWST. So I think in this particular case, we find compelling evidence of a sub-arc second dual quasar rather than a gravitationally lensed quasar with sub-arc second separation. So it's still a very puzzling system, but it's most likely actually a twin quasar, very similar to a symbiotic star situated in a giant rotating disk galaxy. So this slide, I want to highlight the challenge of confirming the rare gems of dual quasars. Or you can think of it as the opportunity to discover another class of known rare gems, which are small-scale gravitationally lensed quasars. So distinguishing between dual and lensed quasars has proven surprisingly non-trivial. And our lesson learned here is that high-resolution deep infrared imaging is the key. So on the left, I'm showing you an example study led by a postdoc, Aaron Gross, who did a detailed multi-wavelength analysis of a sub-arc-second length quasar. And so on the right is a very intriguing example led by another postdoc at Illinois, Junyao Li, where she discovered a quadruply length quasar, which was previously misclassified as either a triple quasar, in a three-way merger, or a dual lensed quasar. And the misclassification was because previously there were only ground-based AO-assisted IFU observations, so the field of view was very small. So it and also not deep enough to detect the much fainter fourth image of that quadruply lensed quasar. So combined together, I think their works really highlight the challenge of confirming the true nature of whatever like different types of rare gems. And in this particular example, so the complicated issues include microlensing and potentially complicated morphology of the foreground lens. So in this case, it's a very disky type of galaxy in the foreground lens, which can be very different from large separation lenses, which typically are these giant ellipticals. Okay, so this slide summarizes the first part of my talk. So I think the main message here is that the future is very exciting, I think, for the field. I want to leave you with something to look forward to. So first, as the first dedicated time domain spectroscopic service, so Sloan 5 is finding more of these subparsec binaries candidates using the radial velocity technique systematically. We also have DESI and other of these spectroscopic surveys that potentially can leverage their spare fiber, for example, to do time domain spectroscopy. So for these brightest RV selected candidates, so actually with future infrared interferometry with Gravity Plus, we can we may able to detect the proper motions and accelerations in order to eventually confirm the binary hypothesis as constraint system parameters. So the synergy of Euclid on the sky and Rubin come online next year will be very powerful for both dual and binary systems. And this will not only help in discovering these rare gems, but also in understanding their statistical studies, as illustrated in the example figure shown at the top. Looking further ahead, so Roman will be able to push both frontiers to lower mass at higher redshift, which are more directly relevant for LISA, as well as some of the planned X-ray missions in future. So I think this is a perfect timing for us EM observers to finally be able to catch up with theorists and gravitational wave community. And the true key again lies in combining the power of these existing and upcoming surveys to really, I think, maximize the potential. Okay, so for the remaining few minutes, so I want to switch gears and touch on exploring the unknown rare gems. So I'd like to start with telling you about building the astro and AI community at Illinois. So one of the key highlights of this initiative is a course that developed launched 5 years ago. So this course is designed to bridge the gap between astronomy and machine learning, focusing on fundamentals of machine learning and big data and providing our students with practical skills and knowledge. So our students will learn about latest advancements in machine learning and how they can be learned to apply it to astronomy data. And our main goal here is to, I think, really build a strong foundation for our students in machine learning and big data, and equip them with the practical skills that they can apply in their own research. And one of the focus is that we, really try to keep up with the latest advancements in these techniques and be able to share them with our community. And this is an example. So I'm showing here is an example student project from our course. So 2 of our talented former grad students proposed and implemented this project, building upon the work that they did in the class. So I think this really is a testament to the potential of this approach of community building, which is, I think, very important for this interdisciplinary type of collaboration. And so it not only enriched the students' learning experience, but also added value to our research community. So to give you a little bit of in-depth look for the student projects, so it addressed a significant problem in astronomy, especially with these upcoming massive deep surveys like Rubin and Roma. So the 2 images show the exact same region on the sky, but seen from 2 different surveys. So it illustrates the increasing complexity of our data as the sensitivity increases. And it really underscores the challenge of deblending or separating overlapping sources of light, a crucial task in image analysis. So the student recognized this challenge and proposed a solution using the latest advancement in computer vision, right? So it turns out that there's a very similar problem in computer science called instant segmentation, also used for autonomous vehicles and medical imaging diagnosis, for example. And the students, in this case, adopted these techniques and apply it to astronomy data. Now, so this study was done as more of a proof of concept type of analysis, in the sense that so they use simulated data as training data set. So to be able to take this to the next level, right? So this slide shows the follow-up work where the student leader here, Grant Merz, so another grad student, pushes this closer to implementation with actual real data. With important help of also an undergraduate student working with the SPIN program at NCSA. So they advanced project by further developing this code to work with real data, incorporating state-of-the-art models, as well as extensive comparison and benchmarking, which are crucially important, I think, to be able to, I think, make the model readily adoptable by the wider community, as well as adding physical inference capabilities such as photometric redshift. And eventually, so as part of the Link Incubator project, so Grant actually interfaced this with the LST PhotoZ pipeline rail, and so it's already available, for the community. The code is highly modular, so it can easily be adapted to incorporate newer models and other components. So I strongly encourage you to check out Grant's talk on YouTube as part of the Link Tech Talks. And it's been an amazing experience working with the Link Incubator team. I want to give a special shout out to the program for their support. So this is my final slide. So to conclude, we're extending DeepDisk to incorporate more self-supervised algorithm for the ability to discover these so-called unknown rare gems. And so these algorithms will be able to incorporate more versatile hierarchical representations so that they'll be able to intricately encode the scene object part compositions inherent in the complex images. And again, our ultimate goal is for DeepDisk to be a community-driven general purpose tool for discovery, helping eventually achieve the goal of discovering the unexpected rare gems. So this largely ongoing work is in a collaboration with computer scientists and information scientists at Illinois. So I want to end by just reflecting on the fact that it's an incredibly exciting time to be part of this field. And we have many related talks and posters in this conference. So and let's all leverage these collaborative projects to continue pushing the boundary. And I look forward to seeing and learning more about the many more exciting discoveries we'll make together in the near future. Thank you.